Good evening everyone. Today I will be talking about the effects of forces in motion, and how they affect an object as it moves through space. We'll discuss the principles of balanced and unbalanced forces, the force of friction, and Galileo's experiment on motion on an inclined plane. Let's begin. Force has the ability to move a body that was previously at rest, like pushing a car that isn't running. Force can also stop a body in motion, like holding back a swimmer in a pool. In addition, it can alter the speed of a moving object, like when a cricket ball is hit. It can even influence the direction of movement, and can change the shape and size of an object, for example, when a metal bar is bent or stretched. All these manifestations of force can be observed in the physical world. Balanced and unbalanced forces are significant in the motion of objects. When two forces operate in opposite directions on an object and equal in magnitude, they are considered to be balanced and the object does not move. But if the forces are not equal in magnitude, they are regarded to be unbalanced and the object will experience a net force which will result in movement. When discussing Galileo's inclined plane experiment, he noticed that when a force is imposed on a body on an incline, the body experiences both balanced and unbalanced forces resulting in movement with various velocities at various elevations. Friction is an important force in our lives, typically acting to resist motion. When an object moves over a surface, friction opposes the motion, which is why a ball rolling on the ground will eventually slow down before coming to a stop, or why a bicycle will slow down and stop when pedaling stops. Constant motion is maintained when the forces acting on it, such as the pushing force and frictional force, remain balanced. If an unbalanced force acts on an object with constant motion, then its speed or direction of motion will change. Once that unbalanced force is removed, the object will continue to move with the speed it had acquired. Galileo Galilei's work was revolutionary in its understanding of the effects of things like balanced and unbalanced forces, force of friction, and the motion of an object on an inclined plane. His famous experiment showed that when an object is sent down an inclined plane, its velocity will increase, and when it goes up the second inclined plane, its velocity will decrease. If the inclinations of both planes are equal, then the object will reach the same height as it started from. If the inclination of the second plane is decreased, the object will travel further to reach the same height. If the inclination of the second plane is made horizontal, the object will travel infinitely, trying to achieve the same start height. This experiment showed that an unbalanced force must be applied to alter the motion of an object, while no force is required for maintaining the same, uniform motion of the object. An object will stay at rest or continue in a straight line if no external forces act upon it. This is known as the law of inertia. This is the first of Sir Isaac Newton's 3 laws of motion that allow us to understand how objects move. The second law of motion states that the acceleration of an object is directly proportional to the net force applied to it and inversely proportional to its mass. Newton's third law of motion states that for every action there is an equal and opposite reaction. These laws help us comprehend the workings of the world around us and how objects interact with each other. Inertia is the property of an object to oppose any change in its state of motion. Examples of this can be seen in everyday situations. For example, when a striker hits a pile of coins on a carom board, the lowest coin moves out and the other coins fall down due to inertia of rest. Similarly, when a coin is placed on a playing card over a tumbler and flicked with a finger, it falls into the tumbler due to inertia of rest. Another example is when a car brakes suddenly and the passengers tend to fall forward due to inertia of motion. Finally, when a person is standing in a bus that suddenly starts moving, they tend to fall backward as their feet move forward with the floor, while their upper body remains at rest due to inertia of rest. An object's tendency to remain in its current state of motion, either at rest or in motion, is known as inertia. This tendency is determined by the mass of the object, which is a measurement of how much matter it contains. The higher the mass, the greater the force required to move or stop the object, indicating that the mass of an object is a measure of its inertia. Therefore, the greater the mass, the greater the inertia. Momentum is a physical quantity that describes the motion of a body. It is the product of its mass and velocity, and it is a conserved quantity, meaning the total momentum of any system remains unchanged despite external influences. The International System of Units, SI, unit of momentum is kilogram-meter per second, or kilogram-meter per second or kilogram ms1. This concept can be exemplified by the difference between a truck and a bullet. Although they are both moving, the truck has a much greater mass and a lower velocity, while the bullet has a much smaller mass and a higher velocity. This explains why a truck traveling at slow speed can cause harm to a person in its path, while a bullet with a small mass can be equally dangerous due to its high velocity. This highlights the importance of both mass and velocity when it comes to the impact of a body. According to Newton's second law of motion, if a force is applied to an object, its momentum will change at a rate directly proportional to the magnitude of the force. This is expressed mathematically as F equals ma, where F is the force, m is the mass, and a is the acceleration. This law explains why heavier objects require more force in order to accelerate, as well as why objects tend to keep moving in one direction even when multiple forces act upon it. This law was formulated by the British physicist and mathematician Sir Isaac Newton as the law of inertia. Newton's third law of motion states that action and reaction forces are equal and opposite. To demonstrate this law, two spring balances, A and B, can be used. When a force is applied by pulling on spring balance A, both spring balances will display the same readings, showing that the force applied by spring balance A on B is equal but opposite in direction to the force applied by spring balance B on A. Examples of action and reaction are all around us. Take for example, when a gun is fired. The bullet is forced out with a forward action, and in turn, the gun is pushed back by a reaction force. This is known as the recoil force. The bullet, being lighter than the gun, exerts a greater force than the recoil force, sending it forward and pushing the gun backwards. Another example is when a sailor jumps out of a boat, he applies a backward action, and the boat in turn pushes him forward due to an equal and opposite reaction. These are just two examples that demonstrate action and reaction in everyday life. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This can be demonstrated through the example of a balloon. When released from its grasp, the force of the air coming out of the balloon exerts an equal and opposite force on the balloon, pushing it upwards. This same idea is applicable to a rocket launch. The force of the burning gases exerts an equal and opposite force on the rocket, sending it upwards. According to the law of conservation of momentum, the total momentum of two objects before a collision is same as the total momentum of the two objects after the collision if there are no unbalanced forces acting on them. This implies that the total momentum of the two objects remains unchanged. As an example, consider two balls A and B with masses ma and mb traveling in a straight line with initial velocities UA and UB, and UA being greater than UB. On collision, ball A will exert a force Fab on ball B and ball B will exert a force FBA on ball A. Let the velocities of the balls after collision be VA and VB. The momenta of ball A before and after collision are MAUA and MAVA, and the momenta of ball B before and after collision are MBUB and MBVB. According to the law of conservation of momentum, the sum of the momenta of the two objects before the collision is equal to the sum of the momenta after the collision. We can see that when ball A collides with ball B, their momentum exchange is equal and opposite to each other, meaning that the momentum of the two balls before the collision is equal to the momentum of the two balls after the collision. This is known as the law of conservation of momentum. The exchange of momentum between two balls during a collision is illustrated in this slide. Thank you for your attention.